All right, let's dive right into this explainer and uncover the sheer engineering brilliance of the Airbus A380's thermal management. When we think about the world's largest passenger airliner, we usually marvel at its sheer size, those massive double decks, or that huge wingspan. But right beneath those floorboards and tucked inside those wings lies a circulatory system of immense power. Today, we're focusing on ATA-29, specifically Part 6. We are going to explore the hidden, highly intelligent, and totally automated defense layers that keep the A380's hydraulic systems from quite literally melting down. To really wrap our heads around the challenge here, we got to talk about pressure. The A380's hydraulic pumps supply fluid at a massive 5,000 psi. That is 345 bar. To put that into perspective for a second, your standard car tires sit at about 35 psi. Pushing hundreds of liters of incredibly thick fluid through complex valves and massive flight control actuators at 5,000 psi creates a very dangerous enemy: extreme, relentless heat. If that fluid gets too hot, it degrades, equipment starts failing, and safety is seriously compromised. So, to beat back this massive amount of heat, the A380 uses a deeply layered defense system. We're going to trace this whole roadmap today, starting with the sheer heat generated by these systems, how the primary air cooling tackles it, the computer brain behind that cooling, the heavy-duty fuel backup, why the fuel system actually has the power to veto that backup, and finally, the overheat alarms that keep the pilots in the loop. Think about the sheer muscle needed to move flight control surfaces on a 500-ton Leviathan. The A380 doesn't just rely on one giant pool of hydraulic fluid to do this. It relies on two primary mirrored networks to carry the load. The aircraft utilizes completely isolated green and yellow systems. We're talking about 585 liters of fluid in the green system and 545 liters in the yellow. And they are strictly walled off from each other. Fluid absolutely cannot cross between them, which ensures that a leak in one doesn't accidentally drain the other. However, both of these independent networks face the exact same thermal enemy, meaning they both require an identical layered cooling defense. When you trace the actual journey of this fluid, it's pretty wild. It all starts at the engine-driven pumps, or EDPs, out in the pylons. Now, the fluid that leaks past the internal moving parts of these pumps, which actually lubricates them, is known as case drain fluid, and let me tell you, it is incredibly hot. So this superheated fluid gets gathered up by manifolds and is immediately sent sprinting out to the wings to cool off before it's ever allowed back into the main reservoir. So where exactly does it go to cool off? Well, that brings us to the front line of this thermal battle, the primary air cooling system. This setup is hidden right inside flap track fairing number 5 on each wing. Think of it as a massive high-tech radiator. It gulps down external ram air through a dual matrix to chill that hot fluid. But, it's Airbus, so they planned for the worst. What if solid ice blocks that main air intake? Boom! Spring-loaded blow-in doors pop open automatically to keep the air flowing. If the plane is taxiing or just moving too slow to push air in naturally, 2 hydraulically driven fans kick in to actively suck the air through. They even put these little seepage bottles underneath the fan motors just to safely catch any tiny eventual leaks. Talk about attention to detail, right? Now, these fans aren't just spinning out there wildly on their own. They're commanded by a highly intelligent central brain known as the Hydraulic System Management Unit, or HSMU. This is really the commander of our thermal defense. The HSMU is incredibly strategic. It thinks sequentially to optimize cooling and save energy. First off, if the plane is cruising faster than Mach 0.45, it completely inhibits or shuts off the cooling fans. Why? Because the sheer force of the air ramming into the intake at that speed is more than enough to chill the matrix. The fans just aren't needed. But on the ground or at lower speeds, the HSMU stages its attack. Once the reservoir hits a mild 20 degrees Celsius, it wakes up the outboard fan. If that fluid keeps cooking and crosses 55 degrees, it calls in the cavalry. The inboard fan, which is the heavy hitter, kicks in to double the cooling power. Behind the scenes, this is all driven by complex if-then logic gates. The HSMU is constantly pulling down telemetry from both the reservoir temperature and the case drain temperatures of those engine pumps. It feeds those signals right through digital OR and AND gates. So it's definitely not just some dumb mechanical switch. It's a continuous, automated software calculation deciding exactly how much cooling the A380 needs at any given millisecond. But that really begs a vital question. What if the primary system gets completely overwhelmed? Say you're taxiing around Dubai in the middle of July, or the Airmetrics outright fails. What exactly is the backup plan? That brings us to the second heavy-duty defensive layer, and it's actually hidden away right inside the engine pylons. If the primary air matrix just can't keep up, the HSMU triggers a secondary route. It forces the scorching hydraulic fluid through a second heat exchanger located right inside the pylon. But here's the clever part. Instead of using air, this exchanger uses cold engine fuel drawn straight from the feed tanks. The cool fuel absorbs the excess heat from the hydraulic fluid, and then that slightly warmed fuel is just sent right back to the engine feed tank. It's an absolutely brilliant, super efficient way to use resources that are already sitting right there on the plane. However, there is a catch. Mixing hot hydraulic fluid with aviation fuel obviously introduces some real risks. You definitely do not want to accidentally boil your own fuel. So, the Fuel Quantity and Management System, the FQMS, steps in as a secondary brain, and it has absolute veto power over this entire backup cooling process. The golden rule here is that the aircraft will never, ever compromise fuel safety just to cool the hydraulics. The FQMS will instantly trigger an inhibition, basically a smart override, that slams the fuel cooling valve shut if certain safety thresholds are crossed. For example, if the fuel quantity in the tank drops below 2,100 kilograms, it shuts off, because a tiny volume of fuel will heat up dangerously fast. If the fuel temperature itself hits 53 degrees Celsius, it shuts off to prevent vaporization, because, boiling your own fuel mid-flight is generally frowned upon. And, of course, if the pilots ever pull an engine fire handle, the system instantly isolates that fuel cooler to avoid feeding a potential fire. So we've got the frontline air defense and the heavy-duty fuel backup, both heavily managed by smart logic. But what on earth happens if both of these layers are breached? This is where the final alarms kick in. The HSMU is always watching the sensors. Isn't just about strong metal, big engines, or thick wings. It's about incredibly intelligent, layered, and automated logic literally protecting the machine from itself. From the primary air scoops to the backup fuel coolers, all the way to the digital veto power of the fuel system, every single component is part of this massive, high-stakes thermal chess match playing out at 5,000 psi. It really makes you wonder, doesn't it? Next time you're cruising comfortably in your seat at 35,000 feet, sipping your coffee, just think about the fierce, invisible thermal battles being fought inside the wings right beneath you. It totally begs the question, what other invisible engineering miracles, what other layers of automated logic are constantly calculating behind the scenes to keep a 500-ton Leviathan perfectly safe in the sky? Keep that in mind on your next flight. Thanks for joining me on this deep dive.